Brains are going to hurt today. I'm going to go over the entire history of our universe, starting from the first thing that we know to present day. There's a link to this entire PowerPoint right up there. You're welcome to open it and follow along with me, but we're just going to go and go and go. You guys are going to be using the information that is in this PowerPoint in order to create your timelines. Your timelines that are going to look something like this. Back to the story of the Big Bang. All of the different galaxies are moving away from us, and we can tell because of their redshift, and it's Hubble that figured that out, which tells us that the universe is expanding. We also see a dark night sky, which tells us that the universe is not infinite in age. It's also not infinite in size. Otherwise, we would see a bright night sky. That was Olber's paradox. We also have Penzias and Wilson, who found the cosmic microwave background radiation, which is actually a picture of the leftover blackbody radiation from the heat given off by the universe because of the Big Bang. We have a bunch of evidence that the Big Bang happened. And as we go backwards in time, the universe gets smaller and denser. Just like the core of a star, as it starts to condense, it's going to start to heat up. We can't get all the way back to time equals 0, because at that point, our laws of physics break down. But we can get to 10 millionths of a trillionth of a trillionth of a trillionth of a second old. And if you write that out in numerals, it's that many seconds. And you might immediately think to yourself, like I did, that's a very random number. Why that many seconds old? And it has to do with math. It has to do with the fact that as you get smaller, temperature is going to go up. And based on our current understanding of quantum mechanics, at different temperatures, quantum particles are going to behave differently. They're going to interact differently. They're going to be going different speeds. They're going to be producing different things. And at different temperatures, as you go backwards in time, we can calculate what that temperature would be like at that particular density. And at that temperature, what would be happening. Interestingly enough, the four fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, start to merge together into a single unified force. We don't have the physics to describe that yet, but we know that it happens at certain temperatures. So we can go backwards in time, and the farther back we go, the hotter the temperature gets. The hotter the temperature gets, the more physics start to break down. And it's at this time that the temperature is at dozens of billions of degrees that our models of quantum mechanics and our standard model of the way the universe works breaks down. So before this time, the temperature of the universe is too hot for us to know exactly what was going on. So let's start our timeline. Hubble's law shows that the universe has been expanding for billions of years. You run it backwards, and at some point you reach an infinitely dense point. We don't know what it is like to be infinitely dense. That's why we don't know what's happening inside of a black hole. But we call that time equals 0, the Big Bang. Time is at 0. What was before the Big Bang? Well, space-time was created during the Big Bang. Time was created during the Big Bang. So there's no such thing as time before the Big Bang. You, by definition, cannot have a before if time was not a thing. This is very difficult for human brains to accept, because as long as humans have been around, there's always been a before. There's a cause and an effect. And our brains don't want to accept the fact that there could be something without a before. My brain doesn't want to accept that. I'm sure yours doesn't. If you ask what is north of Orlando, you might say Sanford or Atlanta or Michigan or Canada or the North Pole. But if you asked what was north of the North Pole, by definition, that doesn't make sense. So asking somebody that question in Orlando makes sense. But asking somebody who lives at the North Pole, what's north of here? They can't answer it. That's the same thing as asking what's before time. Like, there's no answer. Just go with it. You just can't. Just let it be. There's no before the Big Bang, because that's when time was started. If you're not okay with that, There are some videos where other people try to explain what was before the Big Bang. Between time equals 0 and that big decimal, 10 to the negative 43 seconds. So a very short amount of time. Like, it's the shortest amount of time that you can... Very short amount of time. The Big Bang happens. Something causes an infinitely dense point to start expanding. We don't know what that something is. We don't know why that happened. But now something is expanding into itself. Into the universe is expanding into the universe. Like, we don't know what it's expanding into. The universe is just getting bigger. The density of everything in the universe being in something so small means that it's so dense and so hot that our laws of physics don't work. They break down, and we don't know what's happening. We have no clue. We couldn't tell you. We want to. Maybe in the future, when we have a better understanding of quantum mechanics, we might be able to figure this out. But as of now, in 2021, we cannot tell you what was happening between the moment that the expansion started and 10 to the negative 43 seconds. This is what we know as Planck time. Named after Max Planck, it is the shortest possible amount of time that you can possibly measure. It's also the amount of time that it takes light to travel the Planck length, which is the shortest possible length that you could ever measure. More information about that here. Bottom line, we don't know what was happening during this time, other than something started expanding and our laws of physics were different. After the Planck time, the universe was expanding, so temperature was decreasing, and temperature had decreased from really hot to 10 to the 32. I don't even know what number that is. That's a really hot number. And the four fundamental forces that we have today started to break apart from each other. Gravity was the first one to leave. So at 10 to the 32 degrees, gravity is now its own force. The weak force, the strong nuclear force, and the electromagnetic force were all still one force. When physicists use particle accelerators, this is what they're trying to replicate. They're trying to figure out what's going on at this time. You'll notice that a little bit later, at 10 to the 27 degrees, the universes continue to expand, continue to cool down. Then all of a sudden, the strong nuclear force breaks off and is its own force. And then you have the electromagnetic force and the weak force. This is what's known as the electroweak force. I'm getting way beyond the scope of this class into like particle physics, but that interests me, so I want you guys to kind of have an idea. The electroweak force is when the temperature of the universe was 10 to the 15th, which is like 10 trillion degrees or so. So when the temperature was this right here, whatever that number is, a big number, it's pretty hot, all four forces were together. As the universe cooled down, the four fundamental forces started to break apart. Between 10 to the negative 35 and 10 to the negative 32 seconds, so still like right after the Big Bang, not much time has gone by. This is what's known as the inflationary epoch, because all of a sudden the universe inflated, got bigger, expanded by a factor of 10 to the 50, which means that it went from smaller than the size of an electron to bigger than the Virgo supercluster. It expanded real fast. So this little tiny amount of time saw the universe go from smaller than an electron, bigger than the Virgo supercluster, which means it was traveling much faster than the speed of light. Way faster than the speed of light. Which also means that our laws of physics don't work. There's no way to do any experiment in our current universe that could tell us what happened before this inflationary epoch, because physics were different during this time. So stuff could have been happening that we will never be able to even know about. If inflation is as crazy as it seems, why do we think that it happened? Well, there's two problems that this actually solves. The first is the horizon problem, which very simply means that if you look in that direction versus that direction, the universe looks exactly the same. It looks the same in that horizon as it does in that horizon. The second is the flatness problem, which tells us that the universe is very nearly flat. There's going to be more on that in a few days when we talk about what's going to happen in the future, but it has to do with the shape of the universe and how much stuff is in the universe. So let's go through these real quick. Inflation theory solves the horizon problem, which tells us that the universe looks the same on a very large scale. No matter where in the universe you are, it's going to look the same. And what do I mean by that? If you take a look at this photo here, you can see individual strands, you can see little shadows, but if you zoom out, everywhere on this piece of paper looks exactly the same. Our universe is the same way. If you look at a section of the universe, you might see the Virgo supercluster. You might see other nearby superclusters. But if you zoom out, one section of the universe looks just like every single other section. Why would that possibly happen? The only possible solution to that is if the universe was very small and all mixed together and then expanded out very, very quickly. So our Virgo supercluster has individual galaxies with shapes. There are stars in different places, but if you zoom out, the universe does in fact look the same in every direction, no matter where you are in the universe. This is what's known as the cosmological principle. Basically, the universe looks the same in every direction. And the only way that could possibly happen is if the universe used to be very, very small and then expanded out extraordinarily fast so that the makeup of the universe as a whole looks the same as it did when it was little. Another way to think of it is this. If the universe expanded at the same rate without that inflation, what would you see? Well, when you're very little and you have different little sections that look different from each other, such as you do in this circle, as it expands, our observable universe would see different parts of our universe look different. So because when it was little and there were different parts, you could see some green triangles and red squares and blue stars. And our observable universe would tell us that if we looked in this direction, it's going to look different than if we looked in this direction. But we don't see that. Instead, if the universe was little and there was differences, but expanded out extraordinarily fast, so fast that our observable universe is now only able to see one little pocket of the early universe. If you take a look at this, our observable universe, which is inside of the gray, can only see things that are inside of this green triangle section of the universe. Could there possibly be things outside of the visible universe past what we can see? Yeah, probably. But because it expanded so incredibly fast, what we see in our visible universe, the reason that it all looks the same is because it all came from the same little section of the early universe. I feel like I'm doing a horrible job explaining this. So if our early universe had little fluctuations and it expanded at basically roughly the speed that it's doing now, we would expect to see little bits and pieces of all of those fluctuations, and our universe would look different depending on where we looked. But if the universe expanded super fast, as inflation says it did, well, then everything that we can see is basically an expanded version of one of these little pockets, one of those little fluctuations. So it took this little green triangle, spread it out so fast that that's all that we are seeing in our entire visible universe, which is why our entire visible universe looks the same. Could there possibly be things out here past the observable universe? Yeah, probably. If we went far enough, maybe we'd see these blue stars, but we can't do that. So our observable universe all looks the same because it all came from this same little pocket of the early universe.
All of space and time exploded out of a tiny speck billions of years ago, and it's been expanding ever since. We know this as the Big Bang, and it explains a lot of why we see what we see when we look at the universe. But the Big Bang has a problem. The universe we see is too uniform. In the first instance of the Big Bang, some parts of the universe would have been hotter or colder than other parts. But today, everywhere we look, the universe is basically the same temperature. And that shouldn't really be possible. This is called the horizon problem, and we'll get to why it's called that in a minute. If two things are different temperatures and are in contact with each other, those things will balance out and end up with a temperature somewhere in the middle. Two parts of space will balance out if they can exchange energy with each other. They do that with photons, which move at the speed of light. But if space has been expanding for all the billions of years since the Big Bang, photons from one end of the universe have never been able to make it to the other end. Which means if you look east, you should see a different temperature than if you look west. Those parts should never have been able to balance out. They're beyond each other's horizons. And yet, they have the same temperature. The way physicists usually get around this is by saying maybe the universe is much, much bigger than the Big Bang says it should be. If in the early moments of the Big Bang, the universe inflated very rapidly so that the only parts we can see today are the parts that already had balanced out in temperature, then we'd see a universe that looks like the one we actually see. The problem with inflation is why? We don't have a good reason for space and time to speed up and slow down like that. But there's another way to solve the horizon problem. Maybe our understanding of the speed of light is wrong. If the speed of light was faster in the early universe than it is today, far-flung reaches of space could have equalized with each other long ago, and we wouldn't need any inflation to explain what we see. Of course, everything we know about the speed of light says it's fixed and finite, and we don't have great evidence that it was any different in the past. But if we want to solve the horizon problem, we have a tough choice. Either the universe is much bigger than the Big Bang predicts, or the speed of light isn't what we thought it was.
Whenever you see a timeline of the universe, you're going to see the Big Bang, and then it almost always has this little shape right here. This is the inflation epoch. This is when the universe went from very tiny to ridiculously big in a small amount of time, and it's been expanding ever since. It's not been expanding nearly as fast, though. So this little, bell, curve, whatever you want to call it, that is the inflationary epoch, where the universe got real big, real fast. We have actual observable evidence for inflation. Evidence from WMAP, the cosmic microwave background radiation, basically says the clumping of matter that we see, those little fluctuations in this photo right here, these little fluctuations of red to blue, all of those little clumps are consistent with our universe inflating very, very quickly. We've also been able to calculate the average density of what our universe should be, about 6 protons for every meter cubed, and sure enough, that's about what we find. When we look out into space and we count up all of the things that we can see versus how big space is, we get that there's about 6 protons in every meter cubed, which tells us that the universe is flat. That's another thing that our brains have a hard time comprehending, and we'll get to it. But observational evidence actually tells us that inflation happened.
In the beginning of the 20th century, astronomers noticed that galaxies were moving away from each other, and the further apart they were, the faster they moved.
Physicists theorise this meant that the universe was expanding, and that at some point in the past, it must have been very small, dense and hot. They called this idea the Big Bang.
Then in the 1960s, 2 astronomers discovered something called the cosmic microwave background radiation, the CMB, a faint glow or temperature that seems to permeate the entire universe.
This further supported the Big Bang because the only way 2 extremes of the universe could have the same temperature was if they were close enough to each other at some point in the past.
The theory traced the origins of this glow to 380,000 years after the Big Bang, the point where matter started to clump together enough for light to move around freely. But what happened before this, and how did it happen?
Inflation is the best leading theory, or group of leading theories, of how the universe came to be in those early moments of expansion. It's the mechanism, the mathematical details that explain what happens before the 380,000-year horizon of the CMB. It beautifully solved many of the problems with the theory of the Big Bang, but there has only ever been circumstantial evidence for it.
Like any good theory, inflation needed to make a prediction that could be tested directly. In the 1990s, more precise measurements found that the CMB is not perfectly smooth, but has ripples in it.
Inflation theorised that these ripples were the result of quantum fluctuations that were amplified when the universe expanded.
When the universe was that small, the weird world of quantum physics ruled. Energy fluctuated out of nothingness, particles popped in and out of existence, their probabilities all mixed together.
Inflation theorised that the universe expanded so fast, faster than the speed of light in that early time, that these fluctuations created ripples in the fabric of space and time.
These fluctuations expanded and formed hills and valleys in the texture of the universe that allowed matter to clump into the matter we see today.
More precisely, inflation predicted that these ripples would leave a very specific signature of light polarisation on the CMB. Researchers led by John Kovac of Harvard University think they found that signature. we are now waiting for the upcoming observations by the European Space Agency's Planck Space Telescope, which is currently measuring the polarisation of the CMB and is expected to report its findings in October 2014.
This could more firmly establish inflation theory, and we will be able to look back beyond the 380,000-year horizon of the CMB, back to 10 to the minus 36 of a second after the Big Bang.
On that signal in the sky, we may be able to trace our origin.
We were once light.
Then we were ripples in temperature that became stars, galaxies, matter.
And life.
After inflation stops, so the universe expands very rapidly and then it slows down how fast it's expanding. It is still expanding, but it's just not a ridiculous speed anymore. After inflation stops, from this time frame, 10 to the negative 32 to 10 to the negative 11, so still way less than a second, you're going to get photons, little particles of light that collide and produce particle-antiparticle pairs, like electrons and positrons, quarks and antiquarks. This little equation you may have heard of, E equals mc squared, tells us that energy equals mass. Energy like a photon equals mass like a particle, and you can actually go back and forth. If you have enough energy and you smash two photons together, you can actually create mass. You can create matter out of energy. And so two photons with enough energy collide, you're going to get particle and antiparticle pairs. So an electron and a positron, a quark and an antiquark. And what they are going to do is almost immediately, a quark's going to find an antiquark and annihilate back into energy. An electron will find a positron and annihilate back into energy. If you have a photon and a photon that meet, you're going to give off an electron and an anti-electron, or a positron. Then you have a positron and electron meet, and you're going to turn back into energy, back into two photons, two pieces of light, electromagnetic radiation. And what's happening during this entire time is the universe is getting bigger. And as it gets bigger, the temperature is dropping. And as the temperature is dropping, eventually, you're going to reach a temperature where there is not enough energy. The photons do not have enough energy that when they smash into each other to create any new particle-antiparticle pairs. That can't happen anymore. So if you can no longer make particle and antiparticle pairs, well, whatever you've already made is all you have. You don't have enough energy to do that ever again. So all of the quarks will find the antiquarks and annihilate. All of the electrons will find the anti-electrons and they will annihilate. As far as we know, every single time those electrons hit each other, they made one particle, one antiparticle. It was always one of each. And so what should have happened, thank goodness it didn't, what should have happened is that every quark found an antiquark and annihilated back into energy. Every electron found an anti-electron and annihilated back into energy. For some reason, and we don't know what it is, there was more particles than antiparticles. Out of every billion pairs, there was one extra particle than there was antiparticle. So all the particles and antiparticles annihilated back into energy, and every billion times that happened, you were left over with one electron. And every billion times that happened, maybe you got one quark. And every billion times that happened, maybe one more electron. And every single particle that you see in the entire universe, every star, every planet, every galaxy, is made out of that 1 out of a billion that was left over. We don't know why it was particles and not antiparticles. We don't even know why there was more particles than antiparticles. It should have been exactly even, and they should have just annihilated. This is what's known as symmetry breaking. Symmetry is where it's the same on both sides. It should have a particle and an antiparticle, and they should have just annihilated back into energy. But for some reason, there was not symmetry, and there was more particles. Thank goodness, because that's what we're made out of. If everything was symmetric, it would just turn back into energy, and our universe would be nothing but a universe with energy. There would be no matter in it at all. There was 1 out of every billion had an extra little particle, an extra electron, or an extra quark, and every single thing that is in our universe is made out of that extra little tiny particle. So what temperature did all of this stop? About 6 billion degrees. So above 6 billion degrees, you're going to get electrons smashing into each other, creating particles and antiparticles. Once you drop below 6 billion degrees, well, no longer can you make new particles, but you can still annihilate. So a particle and an antiparticle can still come together and make energy. You just can't turn it back into particles. So once the universe cooled down below 6 billion degrees, particle creation stopped, everything, all matter and antimatter annihilated, and there is 1 out of a billion left over. Moving forward, between 10 to the negative 11 and 10 to the negative 6 seconds, the universe is continuing to expand, it's continuing to cool down, and at this point it's now cool enough to form what are known as baryons. Baryons are a scientific way to say protons and neutrons. Before this, it was too hot, and the quarks that were left over from that 1 in a billion particle, antiparticle annihilation, those quarks were just kind of swimming around. But now that it's cooled down, those quarks are going to start to stick together. There are different types of quarks: up, down, top, bottom, strange, and charm. The only two that we need to worry about are up and down, because the other 4 will kind of decay into up and down. But if you have 2 up quarks and a down quark, you get a proton. 2 down quarks and 1 up quark, you get a neutron. At this temperature, or at this time, because of the temperature, you have quarks that are starting to form in these little triplet groups. And they're starting to form protons and neutrons. This time period where baryons are being produced is known as baryogenesis. Baryo meaning baryons, genesis meaning to make. Baryogenesis is the time between 10 to the negative 11 and 10 to the negative 6 seconds after the Big Bang, where the temperature is cool enough for quarks to start to form baryons, neutrons, and protons. Which means every single proton, every single neutron, and every single electron that exist in the universe were formed in the first second after the Big Bang. If you find a proton anywhere in the universe, it was formed during baryogenesis, during this time period. Every single one of them. All of this has happened, and still less than 1 second has gone by. The temperature has cooled, we've gone through a rapid expansion, we have formed a bunch of quarks left over from the matter-antimatter annihilation. Those quarks eventually turn into protons and neutrons. We've got some electrons left over. All of this in less than a second. So now we're going to jump way ahead. Like way ahead. 3 minutes after the Big Bang. Before this time, before 3 minutes have elapsed, photons still had enough energy to break apart any sort of atomic nucleus. There's absolutely no nuclei before the universe was 3 minutes old. It was basically just a bunch of protons and neutrons and electrons running around in a big, super hot subatomic particle soup. After about 3 minutes, the temperature of the universe has actually cooled down to about 10,000 degrees. 10,000 degrees Kelvin is about the temperature of, I don't know, an A-class star. So it's not the trillions and quintillions of degrees hot that it was at the very beginning, but it's still pretty hot. The entire universe is about 10,000 degrees. And finally, that means that the particles have slowed down enough, because they're cool enough, where protons can start to stick together, and you can start to form helium. You can start to throw some neutrons in there. All of a sudden, you get elements that are not just hydrogen. You start to make some helium. You also get some neutrons sticking to protons, which means you're making deuterium. There's a little bit of tritium in there. This is when atomic nuclei start being formed. So we call this nucleosynthesis. This is the beginning of atomic nuclei. Most protons kind of stay by themselves, which means that they're just hydrogen. Some of them will stick together to become deuterium, some tritium, some helium, but all of them are missing their electrons. It's still way too hot for electrons to latch on to those protons. You can't form a full atom yet. Remember, an atom has protons and neutrons in the nucleus, and electrons are on the outside. It's still way too hot. So all of the electrons are stripped from these atomic nuclei. They're basically causing every atomic nuclei in the universe to become an ion. So there's no atoms yet, but you do have atomic nuclei. And if you remember when we talked about spectroscopy, what is it that causes those dark lines? That's when electrons absorb a photon. So electrons are now in the universe just flying all over the place. They're not attached to any atom yet. They're just free floating, which means they are absorbing every photon of light that exists. So a photon of light actually can't travel more than a very short little tiny distance before it is immediately absorbed by one of these electrons flying around the universe. So we call this time period the opaque epoch, because light can't travel through it. If an object is opaque, you can't travel through it. Transparent means you can travel through. So if you were to go back in time and somehow not die because of the temperature, you could actually put your hand right in front of your eye, and the light would not go from your hand to your eye. You couldn't see anything. Even though there is a ton of photons running around, because they cannot travel, you wouldn't be able to see anything. So we call this the opaque epoch. The entire universe is pitch black, even though there's a bunch of light in it. Jumping ahead about 20 to 30 minutes after the Big Bang, and it's now cooled down to the point where nucleosynthesis stops. You don't get any more tritium formed, you get no more deuterium formed, you get no more helium formed, because the atoms, the protons, are not moving fast enough to stick together anymore. You're basically unable to do nuclear fusion. With no more nucleosynthesis happening, the amount of hydrogen and helium that you have at that point is what you're stuck with. And it ends up being about 75% hydrogen and about 25% helium. And no more of that hydrogen is going to get turned into helium at the beginning of the universe. It will later on in the core of stars, but at the beginning of the universe, you have about 75% hydrogen and about 25% helium. We actually worked these percentages out using math, using basically what we know about how atoms interact with each other. And then when we go and look at the most distant galaxies, which means those stars and galaxies were the first to ever form in the universe, they have that exact ratio of 75% hydrogen, 25% helium. So this is just a little bit more evidence that what we think happened, when we look in the sky, we see evidence that that is correct. We calculated that this was the ratio of atoms, and then we look in the sky way far away, and the first stars to form, they had that exact ratio. Let's jump way ahead, about 380,000 years after the Big Bang. The universe has now cooled down to about 3,000 degrees. And at that temperature, the electromagnetic force between a negative electron and a positive proton are strong enough to have the electron stick to the proton. This is when we are now starting to form complete atoms, where you have protons and neutrons in the nucleus, and then you have an electron orbiting around it. Because the electrons are now stuck to these nuclei, they're part of atoms, they're not absorbing light anymore. And now photons are able to travel throughout the universe, which means whichever direction that photon was traveling, it continued to travel with the energy of a photon that was released from an object at 3,000 degrees, the temperature of the universe at that time. And now we can actually detect those photons as they hit some of our telescopes. And those photons that started traveling right as electrons were captured by the atomic nuclei, those photons are the cosmic microwave background radiation. They started with an energy of about 3,000 degrees Kelvin, and because the universe has slowly been expanding and stretching, those wavelengths have stretched out until now they're in the microwave part of the spectrum. To put it another way, they now have the energy of radiation that would be given off by a black body at about 3 degrees above absolute zero. So the cosmic microwave background radiation is actually a picture from 380,000 years after the Big Bang, when light was finally able to travel. And we call this time period the epoch of recombination, because it's when electrons combined with the atomic nuclei to form atoms. My personal opinion is that it should be called the epoch of combination, because it has never combined before, so it's not recombining, it's just, electrons and protons combining together for the first time. But all of my letters to professional cosmologists have gone unanswered, and they have not changed the name. So the epoch of recombination is when electrons attached to the protons or atomic nuclei to form atoms. Light was able to travel through the universe. That's where the CMB comes from. And at that time, those electrons had the energy of about 3,000 degrees. What would that look like if we could go back there? What does a photon with the energy of 3,000 degrees look like? It's in the orange part of the spectrum. So if we could go back there and not get burned up because the universe was 3,000 degrees, the universe would be orange. Every photon of light that was traveling through the universe is the color orange. So the universe used to be orange. That's just weird to think about. The universe now is black if you go up into space. It used to be bright orange. Alright, let's move ahead from 380,000 years to between 3 and 400 million years. This is when the first ever stars start to appear. Regions that were a little tiny bit more dense. And those are the fluctuations that we see in the CMB. If you're a little bit more dense than this area over here, gravity is going to start to coalesce some of that hydrogen and helium. And as it coalesces, you're going to start to get galaxies forming. And from the big clouds of gas and dust in these galaxies, you are going to get to have stars start to form. So before about 3 to 400 million years, there was not a single star anywhere. There just wasn't enough time for those gas clouds to coalesce after the Big Bang. It took about 3 to 400 million years to have the first star turn on. Because there was no stars and the universe had cooled down so that the light was out of the visible part of the spectrum, it was pitch black. This is known as the dark era because the universe was not glowing with black body radiation anymore. There was not a single star that had formed anywhere in the universe. So if you travel back in time to this point, you could just look around and you would not see a thing. There would be stuff there, but you couldn't see any of it because none of it was emitting any sort of visible light. So before this point, between 3 and 400 million years, completely dark, completely black. This is the dark era. After about 3 to 400 million years, stars start to begin to form. So if you were back there, all of a sudden you might see a little star wink on. Over here, a little star starts to give off light. And you would start to see stars beginning to form, and it's the very first starlight to ever travel through the universe. And things went on like this from about 400 million years to about 10 billion years. So the universe is 13 billion years old. So up until about 3 billion years ago, the universe was expanding and stars were forming, galaxies were forming, star clusters, black holes were forming, there is supernova, you're getting second generation stars, maybe some third generation stars, planets were forming, maybe aliens lived and died and now they're gone. It's just the universe being the universe. The universe was expanding, but because of all the stuff in it, it was slowing down. So the expansion of the universe was actually slowing down because gravity was dominating the expansion. The gravity of all this stuff in the universe was slowing down how fast things were moving away. If things just continued like that, that expansion would slow down and eventually gravity would start to pull everything back together. But about 10 billion years ago, even though expansion was slowing down, something happened. We don't know what it was. We don't know why, how. That slowing down started to speed up. And that's where we're at today. So the expansion of the universe was slowing down, but now it is speeding up and it's getting faster and faster each and every day. Why? Dark energy, anti-gravity, cosmological constant, whatever you want to call it. The universe is now getting bigger, faster and faster and faster each and every day. What is dark energy? We're going to look at that more in depth in a few days, but we don't know. It's anti-gravity. It's the opposite of gravity. It's pushing everything farther apart faster and faster. We are also, in a few days, going to take a look at what could possibly happen in the future, way in the future. But based on our current measurements and observations, what do we think is going to happen to everything in the universe long into the future? This graph is logarithmic, not only with the temperature scale, but also with the time scale. This chart tells us that as the temperature of the universe goes down, different things are going to happen. You can form helium. That's the nucleosynthesis part. You have the emission of the cosmic background microwave radiation. You have the dark ages, which was before any stars existed. You have the first stars starting to pop up. You have galaxies forming, and now you have modern galaxies, which, all different sizes, shapes, colors. But as all of this is happening in our universe, the temperature is continually decreasing. It's getting colder and colder and colder and colder. You'll see a lot of different timelines of the universe. Many of them had this inflationary epoch where it got really big really fast. This one actually has the expansion start to slow down, Then about 3 billion years ago, that expansion is now speeding up, and it has little pictures of what's happening in each time period, as well as some descriptions of what's going on. And that's where we're at today. But